So continuing where we left off, I waited for a second. You were a little slow. Sorry there, mister. Let's see if we can apply some of what we've learned already. Come here. There we go. I'm having a little trouble with my pen, by the way, so I apologize in advance. I'm having to write things 2 and 3 times. Example 4. Hey, Space Shuttle has a mass of 2.03 times 10 to the 6th kilograms. It does, and you're going to find we're going to be using scientific notation a fair bit in this unit because stuff has big masses sometimes. Suck it up, that's life. If each engine is capable of exerting a force of 12.5, what does a capital M stand for as a metric prefix? What does that one mean? Meganewtons, which it does, I looked it up. A, what's the maximum acceleration of the space shuttle? Note there are 2 engines. Okay. What's A asking me to find? Acceleration. What have they given me? Looks like they've given me a mass. Yes? And it looks like they've given me a force. Now, there's 2 engines, so I'm going to multiply by 2. How big is the force? 12.5 what? Mega means replace it with a 10 to the 6th, a million. It's going to be 12.5 times 10 to the 6th newtons. That's 12.5 meganewtons, but 2 engines, Emma. Emma, what's this question asking me to find? Hey, is there an equation that has acceleration, force, and mass in it? There is. Why, it's this one right here. How would I get, oh, this is why I taught you formula manipulation last unit. How would I get the A by itself? Here's a whole new equation which I don't need to memorize. How would I get the A by itself? Divide by M. Yes? So can we do that? We can say A equals F over M. These are the numbers right at ignition. I'm assuming you've all at least once on TV as a movie seen a space shuttle launch or a rocket launch. So right when you see that big plume of smoke, this is the numbers. Oh, the force is going to be 2 times 12.5 times 10 to the 6th over 2.03 times 10 to the 6th equals, you probably, if you haven't done scientific notation for a while, you may want to get your calculator out and practice this. Is there more than one number on the top? I think I'll put the top in brackets. I might not need to, and in fact, in this case, I don't, but better safe than sorry. Is there more than one number on the bottom? A 2.03 and a 10 to the 6th. I'll put the bottom in brackets as well. So it's going to look like this. 2 times 12.5. Hey, our calculators had a shortcut for times 10 to the power of. What was that shortcut, Jake? That was your scientific notation button, whatever your calculator looks like. Mine is a little E thing there. And I just have to put the exponent. I don't need to hit the times. I don't need to hit the 10. I don't need to hit the to the power of. It takes care of all that for me. Divided by, oh, the divided by didn't go. Divided by, bracket, 2.03, scientific notation to the power of 6. What's the acceleration? What'd you get? 12.3 units acceleration. By the way, who remembers what's 1 g of acceleration? 9.8. This is only about 1.5 g's. Not bad. You do far more than this on a roller coaster.
Wait a minute. I heard that the astronauts, they like feel a whole bunch of g-forces.
Not right at launch. B. Why does the maximum acceleration change as the engines burn? Why does the acceleration go up as the engines burn? Mr. Biggin, impress me. What?
The mass is changing.
Getting bigger or getting smaller? So if acceleration is force divided by mass, if that gets smaller because you're burning fuel, but the engine thrust, the force doesn't change, what happens to your acceleration? Your answer. If you divide by a smaller number, what happens to your answer? It gets bigger. Therefore, A increases. So after about 60 seconds, oh, probably now you're feeling around 4 Gs.
What's that inside the A? It's like
3 dots? What do 3 dots mean? It's a therefore. Anytime you see a therefore, make sure you know what it's there for. That's both a joke, but also being very serious. Anytime you see a therefore, that probably means there was some explanation, and this is the conclusion. So 3 dots in a triangle. Haven't I showed you guys that one before? Oh, good gosh, I need to nerd you guys out. Therefore, you'll find that one right away in university all the time. That's become fairly universal. Therefore, acceleration. And my abbreviation for increases is an arrow pointing up. How would I show decreases or get smaller? An arrow pointing? Yeah. Can we go with that? Yeah. How does Newton's second law explain why a sprinter might want to wear lightweight shoes? You know what? Let's write this again. All right? Now, Jeff, let's suppose you're Usain Bolt, and you have trained as much as you can possibly train. Your legs are incapable of exerting a bigger force. You've maxed out your force. If we want to increase acceleration, and we can't change the F because you've lifted weights as much as you can, hey, what else can I change in this equation? The mass of my shoes. And if the mass gets smaller, same force, what must happen with the acceleration of my feet? Yeah, same idea. As M decreases, A increases. That's, hey, any bit of mass you can get rid of. It's why the track suits are as minimalistic as possible and as light as possible. Okay? Oh yeah, anything you can get rid of, totally. It's why the trend in the past 20 years for almost all sports equipment has sports equipment got heavier or lighter? No kidding, lighter. It's not necessarily that, say, looking at football, the players are so much bigger and stronger and faster than 20 years ago. It's they're wearing way lighter equipment, so of course they seem faster. They're not carrying as much as they were 20 years ago. They may be fast. I mean, the training's gotten better, the nutrition's gotten better too, but a lot of it is just straight equipment. There's another reason why you want things to be lighter, and it has to do in terms of energy. We'll talk about that about 3 weeks from now. Gonna make it, Zach? You sure? Okay. Turn the page. Newton's third law. So Newton's first, the law of inertia. Objects at rest tend to remain at rest. Objects in motion tend to remain at motion. Okay, you know what? Things want to keep going in a straight line at a steady speed, and if they're not, there's an outside force. Mass resists change. There's a whole bunch of ways to phrase Newton's first law, but it explains outer space. It explains why seatbelts save lives. Newton's second law, F equals ma. It's the equation. Newton's third is the one that is both the most difficult to wrap your brain around, but actually influences you the most. It's traditionally phrased as, Mr. Goulet is fond of quoting it, for every action there is an equal and opposite reaction, which is about as confusing as you could possibly phrase it. I wrote down here, because that was my first, no pun intended, reaction when I saw this. Here's Mr. Dueck's handy-dandy version, my shorter version. Forces come in pairs. Anthony, forces come in what? Pairs. You cannot have a single solitary force by itself. It's impossible. Really? Yeah. Or, you know what, if I want to write it mathematically, Valoria, I would say this. The force of object A on B is the same size as the force of object B on object A, but in the opposite direction, so I'll call it negative. Bet you're awake now, though, aren't you? Uh-huh. So we've done a bunch of examples of Newton's third law. Oh, Kyle, gravity's pulling you down. Yes, we've agreed on that. Are you sinking down? Your chair and part of the floor, because your feet are touching the floor, are applying exactly the same force as gravity. And I know it's exactly the same because are you sinking into the ground like quicksand? Are you flying into the air like Superman? You're not accelerating, then the net force must be 0, which means my forces must be balanced. If I know the force of gravity, I can calculate the force of the chair. It's going to be the same size. If you lift your feet off the ground and it's all on the chair. Okay? How does Newton's third law help explain why it's difficult to walk or drive on ice? Friction is much smaller. The friction force is much smaller. And so if you demand the friction force be big enough that you can turn, I'm sorry, forces come in pairs. It can only be so big. You saw when we had Tawny and Shaq, even though Tawny wanted to try and resist Shaq, trying to apply a bigger force, and even though Shaq could do a bigger force than 200 newtons, I'm sorry, forces have to come in pairs. Or if we really want to take the thought experiment to the ultimate level, instead of having Tawny pushing against Shaq, what if we had Shaq pushing against a feather hanging from the ceiling? If you could put 1,000 newtons of force out, hopefully you can see there's no way that feather could apply 1,000 newtons of force back. In fact, right when you get to about 5 newtons of force, it's going to start to have an unbalanced force and accelerate, and there you go, we're over. Okay. How does Newton's third law help to explain why professional boxers wear boxing gloves? Oh, this I can write as an equation. F, hand on face, equals F, face on hand, but negative if we bring in the vector directions. And by negative, I mean opposite direction, same magnitude. Okay. Those of you that play sports, if you really think about it, anytime you're doing any kind of movement, it's the opposite. Basketball players, if you're in a defensive stance and you want to slide to the left, think about it. Which way do you actually apply force? Hard to the right. Oh, and what you're doing is you're using friction to push you to the left. You're wearing better shoes to try and increase friction if possible. And if you don't do it right, you'll slip. It means you tried to get too much of friction and it's saying, sorry, I can't do that. Forces, I can't come in that pair. So you're going to slip and you won't accelerate. Got some nice examples here.